Section 4-9 is on related rates. And again, the objective of this section is given a problem in which several quantities vary. Predict the rate at which one of them is changing when you know the other rates. So again, the title of this section, Related Rates, tells me that I'm going to end up with a relationship, and it's a relationship of rates. And the way that we're going to get rates into this problem is with a derivative. I know the rate of change is a derivative, and so I'm going to end up with a relationship between these rates. I'm going to come up with an equation that involves some unknowns, some variables. By taking the derivative of that, I get the relationship of rates. That's what these are called. Let's take a look at another example here in this section. This is on page 174 there. It says an airplane is flying 600 miles per hour on a horizontal path that will take it directly over an observer. The airplane is 7 miles high. And for part A, it says to write an equation for the rate of change of line of sight distance c in miles between the observer and the airplane in terms of the horizontal displacement, x, in miles from the observer to the plane. All right, so let's draw a picture. They gave you a sketch of what this kind of looks like, but I'm going to sketch it over here as well. We have a right triangle. This is you over here on the ground. Here's your plane up here. And your plane is flying in this direction. And they tell you it's flying in that direction at 600 miles per hour. And they tell you the plane is 7 miles off the ground. Oops, we'll just say mi for miles. And they say that you're standing x miles from the plane, and then the distance from you to the plane, that straight line distance there as you look up towards it, is z. All right, so there's a picture of what we've got going on here. Now again, if it's helpful to draw a picture, do so. That wasn't part of our guidelines, but in many problems you'll find that sketching a picture might help you out there. Still, we want to write down what we know and what we're trying to find. All right, as far as what we know, they told us one rate. That was the 600 miles per hour. And you'll see that as our plane is moving closer towards us, that means that this distance x is changing at the exact same rate, because that's the plane's horizontal movement, so that horizontal distance x is changing. So in other words, it's dx dt is the rate that we know. The change in x with respect to time is the 600 miles per hour. Now, again, anytime they give you one of these rates, you got to carefully go back and consider, is this value, is this rate a positive rate or is it a negative rate? They will not tell you that. Sometimes they'll give you hints by talking about that the value is increasing or decreasing. That tells you whether it's positive or negative. And other times you got to look a little bit more closely at the problem to determine that. And this is one of those cases where you got to look closely at what's happening here. So as the plane is moving towards us, you can see this distance x is decreasing. That distance the plane is from us is getting smaller, so x is decreasing. So if x is decreasing, then its rate must be negative. If x were increasing, then the rate would be positive. All right. Now as far as what we're trying to find, read part A again of this. It says, write an equation for the rate of change of the line of sight distance z. So we're trying to find the rate of change of z. That's dz dt. And they say to do that in terms of the horizontal displacement x. So I eventually want to get this in terms of just x. But again, by laying this out, by putting down exactly what we know and what we're trying to find, this helps me see what kind of an equation I need to come up with to start off with. Sometimes they've given you the equation to start with. In this case, they did not. You have to come up with that. So I can see that I need an equation that relates x and z. So over here on the right, I've got a right triangle. And I've got x and z are two sides of that triangle. The third side is known as 7 miles. So that looks like I could use Pythagorean Theorem to come up with a relationship between x and z. In fact, z squared would be equal to x squared plus 7 squared. That's what Pythagorean Theorem tells us. And so this guy right here, this is part A. This guy right here is what we want to take the derivative of. We're going to take the derivative with respect to t of z squared is equal to x squared. I'm going to write this plus 49 instead of 7 squared, but you can write it either way. And I like writing that as d dt out front, so I realize I'm taking the derivative of that equation. All right, let's tackle the derivative of this thing. On the left side, we've got z squared, so follow chain rule as I take this derivative. It's 2 times some quantity raised to the first power, and chain rule says you substitute in the inside function, that's z, times the derivative of the inside function, that would be dz dt. And over on the right side, we're going to do the same thing for x squared. It's 2 times something to the first power, and chain rule says you substitute in the inside function, and then we multiply by the derivative of the inside function, that is dx dt. And then finally we add on the derivative of 49, which is a constant, so its derivative of course is 0. All right, we're trying to find out what dz dt is equal to, so let's divide by the 2z over here on the left. So we'll have 2x over 2z times dx dt. We'll write it like that. Notice that the 2's here, of course, are going to cancel out. So we can rewrite this as dz dt is equal to x over z times dx dt. Now again, we wanted to write this in terms of just x. So I need to come up with something for z, and I also need to come up with something for dx dt. Now the rate, the dx dt, that's the easy one. If I go back up here, that's part of what we know. We know that rate, so I know that's the negative 600. What I need to do is I need to come up with a way to substitute in for z. So if I come back here to this original equation that we had here, and we'll just rewrite it. If I solve this thing for z, I know z is equal to, it's actually technically plus or minus, the square root of x squared plus the 7 squared, or I'll write that as 49. Now the z is the hypotenuse of our triangle there. That's the straight line distance between us and the plane, so it's going to be positive. So I don't need to worry about the negative part of that root. But that's my substitutions then. I can rewrite this then as x over the square root of x squared plus 49 times the negative 600. Or I guess if we want to move the negative 600 into that numerator, we could write it as negative 600x divided by the square root of x squared plus 49. There we go. All right, so now that's dz dt. Part B of this thing says to plot dz dt as a function of x squared, or excuse me, of x. So let's jump back over to our calculator here and bring that up. And in y1, let's go ahead and put in the equation we came up with for dz dt. It was negative 600 x divided by the square root of x squared plus the 49. Oops, 49. And for our window, again, x is measuring the distance that we are from the horizontal distance that we are from the plane. So I'm going to go negative 20 to positive 20 for this graph. And I guess I'll put a scale of 5 in here. And for the y values, I'm not totally sure what we need. So I'm going to go to my table, and I'm going to start it out at negative 20. And I'll just go ahead and leave it changing it by 5 there. And if we look at what y values we had 566, and then it starts decreasing, and it really decreases over that last little bit towards 0. And then it increases, well, it's the same y values here except for they're negative. So looks like if we go from like around negative, let's say from negative 600 there to positive 600. Let's graph that. So there's our sketch of this derivative function that represents the rate of change of that line of sight distance. All right, so for part C now, it says how fast is z changing when x is equal to 10? All right, so let's try that out. Oops. So for part C, when x is equal to 10, the question is what does dz dt equal? And I already have the equation for dz dt in my calculator, so I'm just going to go back to my calculator actually and use it to evaluate this. I can go to the table, or I can do it right here from this home screen here, or from the graphing screen, and just trace it to x equals 10, and we get to negative 491.539. Negative 491.539. And this is going to be in miles per hour. The Z is measured in miles, and the T is measured in hours. So this is miles per hour. And they also asked in this problem to evaluate dz dt when x is equal to negative 5 miles. And it says that is when the plane is 5 miles beyond the observer. So when x is equal to a negative 5 miles, we end up with dz dt is equal to, let's go ahead and punch that into our calculator. We'll just trace it to that point again. So we get 348.743. That's in miles per hour. And the last thing they ask us to do there is interpret the answer. So if you look at the answers we got there, first of all, the first one was negative 491.539 miles per hour, basically a negative 500 miles per hour. And the reason why it's negative is because the fact the plane is still out in front of us, so it's moving towards us. So just like dx dt was a negative 600, turns out that dz dt is also a negative value because of the fact that that straight line distance to the plane is decreasing. And if the distance is decreasing, that means the rate must be negative. If you look at what's happened at x equals negative 5, now here the plane's already gone past us. So because the plane has gone past us, that means the straight line distance between us and the plane is now increasing. So because z is increasing, its rate must be positive, roughly 350 miles per hour. All right. And the last part of this says to interpret the graph in part B when x is equal to 0 and when the absolute value of x is very large. So if you look at our graph, let me just flip back to the calculator here so we can see that. Here's our graph. And I can see that as x goes to 0, in fact, we can even trace it there. If I trace this to 0, you'll see that it goes right through the point x equals 0, y equals 0. Or really, it's dz dt equals 0. And so when the plane is directly overhead, let's just write that down, that when x is equal to 0 miles, dz dt is equal to 0 miles per hour. In other words, the plane is not, the distance between the observer and the plane is not changing at all. Its rate is 0. And the reason why that is if you, again, look at our rates that we got previously, when the plane was out in front of us still and coming towards us, the rates were negative. And then all of a sudden when the plane goes past us at negative 5, the rate is positive. So somewhere it has to go from being negative to positive. It has to transition through 0 in order for that to happen. So it turns out that right at x equals 0 and the plane's right overhead, that the rate is 0. And then finally, they also ask when x, the absolute value of x is very large. So again, from the graph here, they ask us to interpret this. You could also use a limit to interpret this thing. If we let x go to infinity or negative infinity, we'd see something similar happen. But just from the graph, as they let x go get bigger and bigger and bigger, the further you go to the right, it looks like that this function here is approaching negative 600. All right, it looks like it has a horizontal asymptote the further we go out. In fact, we can check that here to verify it. Let's just find the limit of this thing. If we take the limit as x goes to infinity of our function, the negative 6, that's the derivative function, dz dt, negative 600x over the square root of x squared plus 49. And when you're dealing with a limit that goes to infinity, many times multiplying by 1 over x or 1 over x squared or something like that is actually a really nice thing to do because 1 divided by infinity is 0. So if I can have things like that show up in the problem, those are pretty nice to work with. So let's see what happens here. The numerator becomes just negative 600 when I multiply by the 1 over x. In the denominator, I'm going to push that 1 over x inside the square root. So of course, in order to put it inside of the square root, I have to square it. So 1 over x squared becomes 1 over x squared times x squared plus 49. And let's go ahead and distribute the 1 over x squared through those parentheses there in that root. So we get negative 600 over the square root of x squared over, x squared over x squared is just 1. And when I distribute the 1 over x squared times the 49, I get 49 over x squared. And again, that's pretty nice. When I let x go to infinity there, 49 over a really huge number is heading towards 0. So if I evaluate this limit, in the numerator, I get just a negative 600. In the denominator, I have the square root of 1 plus, again, the denominator there is going to infinity. 49 over a really big number is going to 0 then. So the square root of 1 is 1, so we have a negative 600. This will be miles per hour. And again, you can see that graphically. We said that appears to be what happens graphically. Oops. Let me switch over to my graph. As x gets further and further to the right, you can see it's approaching a horizontal asymptote there of about a negative 600. On the other side, you could do the same thing with letting x go to negative infinity, and it must approach a positive value of 600 there, it looks like. Okay. All right, and that's the end of that question. And so that's the end of our notes here.